Welcome back to section 5.3, day 2. We're going to be finding the derivative of an inverse. Now the notation they'll give us to have us find the derivative of an inverse, they'll actually kind of put it in the order we need to find it in. So they'll have in parentheses f -1, which means inverse, and then they'll have that one little hash mark for derivative. So what we'll want to do is find the inverse, and then we'll find the derivative. If we can solve our inverse for y, we'll do that explicitly. If we can't solve it for y, we'll find the derivative implicitly. So first things first, we will find that inverse. So switch those x's and those y's, and then solve for y if possible. So I'm going to subtract 2, and then I'm going to take the cubed root. I'm going to rewrite using my handy-dandy function notation. And I can leave it as the cubed root of x minus 2 or x minus 2 to the 1/3 power. Now I'm going to find the derivative. I love it when you can solve for y because then you can use the nice pretty notation. When I find the derivative, I'm using the chain rule, so power comes down in front, subtract 1 from the exponent, and then multiply by the derivative of what's inside, and then do simplify because we will be working with these, and the more simplified it is here, the better it's going to be for you to plug in values and so forth. So there's the inverse's derivative. Not too bad. Yeah, until now. So when I go to find the inverse of number 11 here, I'm going to switch my x's and my y's. And then I realize, wait a minute. I can't solve it for y, but that's okay. I can still find the derivative. I just can't use the handy pretty notation. So I'm just going to put the fact that I'm finding the derivative. Well, when I take the derivative of x, it's 1. When I take the derivative of y, it's with respect to x. So every time I take the derivative of y, you got it. You've got to attach dy over dx. So 5 dy dx. The derivative of 3 is just 0. So I need to factor out that dy dx. I've got 6y squared plus 5. I'm going to divide through. So I end up with my inverse's derivative. Once I finish, I can go ahead and use my notation, because I have indeed solved for dy over dx, and that's what this notation is. You had your inverse, you found the derivative, so this is what we end up with. So let's just do another example just to make sure we got the swing of things. All right, so find that inverse. It's going to be a game show one day. It's going to catch on. 5y minus sine of 2y. I need to find that derivative. I can't solve it for y, so the derivative of x is 1 equals the derivative of 5y is 5 dy over dx minus the derivative of sine, which is cosine of 2y, times the derivative of 2y, which is 2 dy over dx. I'm going to factor out that dy over dx. So I end up with 5 minus, I'm going to move that 2 in front because I don't want it getting caught up in the angle. And then I'm going to divide through. So this is my dy over dx that I've just solved for. Ooh, she's getting sloppy, kids, sorry. So I'm going to go ahead and write my notation. I always want to check because I just want to write that f inverse, but make sure it's actually f before you start calling it something else. Nobody likes to be called something else. 5 minus 2 cosine of 2y. So there's my inverse's derivative. Now we can kind of see that there's probably going to be an issue. On previous slides, on the slides from yesterday's, I had you find h inverse of 2. I had you find f inverse of -1. Okay, well that's going to be a problem because if you notice our notation, here's an x. So this number belongs in for x's, but what do you notice about your equation? Your equation has y's. that's going to be a problem. So they're going to ask us to find the inverse, find the derivative of that, and then plug this value in for all your x's. Now you can kind of see the problem. So that right there is your x value. Well, that's not going to be a problem if you can solve for y. So let me show you. We're going to go ahead and find the inverse. So when I do that, switch the x's and the y's just like we've been doing for the last couple minutes here. So I'm going to subtract 1, and then I'm going to take it to the 5th root. So I have solved this for y. Okay, so that seems pretty nice. Okay, now I've got to find the derivative. So when I find the derivative, notice I'm using my proper notation so people know what I'm finding, and frankly, I know what I'm finding. So 1/5 times x minus 1 to the negative 4/5 times the derivative of what's inside, which happens to be 1. So this little guy, and I want to keep writing my notation so you know where I'm plugging things in. There's 5x minus 1 to the 4/5 power. Okay. Now what they want me to find is the inverse's derivative when x equals whatever they put over here. So this is my x value. So that is what I'm going to put right in there. So I'm going to find my inverse's derivative at 33. Well, notice on my equation here I have x's, so I'm going to put that 33 in for every x I have, and I'm going to simplify. I end up with, 1/80. So they're going to give me the x value to plug in for all the x's in my inverse's derivative. Well, you've probably already looked at your notes, so you already know there's going to be big trouble. All right, so let's talk through this example here. Looking at this example, you can already tell things are not going to go well. When I find the inverse, I'm not going to be able to solve for y. Well, that's okay, because we were still able to find the derivative, the inverse's derivative. We did that on 2 problems. Okay, so in order to find that inverse, we switch the x's and the y's. So there's my inverse. And then we find the derivative. Okay, so this is my inverse's derivative of x. So the number they give me, that 2, that is my x value. Now the problem is when I look over here at my derivative, there's no x's. I've got y's. So that means I need to find out what my y value is. So remember your function, this is my inverse. Okay, so my x value is 2. I need to find out what my y value is. Question mark. Don't know what it is. But remember, when you're looking at your regular function, that switches. So 2 is actually my y value for my original function. So what I want to do is go back to the original function and put 2 in for the y value and solve that. Well, this isn't something that we can solve without the use of a calculator, so we'll put it in our calculator and we find out that the x value is 1. Okay, so what we just found, let me use green, okay, is that the x value when y is equal to 2 in the original function, it's 1. So this I know now is 1, so that means the y value in my inverse is 1. I know you're riveted, aren't you? You're like, oh my gosh, this is so fabulous. So now I can go back to my information here. Go back to my derivative already in progress. I now know what the y value is for my inverse. It's 1, so I can plug that in. So the answer finally is 1 over 5. So when you can't solve for y, you are going to be in a pickle. That's why I used green, the color of pickles. So let's look at one example all by ourselves. All right, so I have my function here, and I am 1 to 1 because I'm in between 0 and pi over 2, so we know cosine's 1 to 1 in that interval. So I'm going to find my inverse. We want to get as many points as possible, so we are not going to panic. We switch our x's and our y's, so this is the inverse. Now I'm going to find the derivative of that inverse. So I take the derivative of x, which is 1. I take the derivative of cosine of 2y, which is going to be negative sine of 2y times the derivative of 2y, which is 2 dy dx. I'm going to solve for dy dx, which means I'm going to divide through by all of that craziness. 1 divided by 2 negative sine of 2y. So what I have here is the inverse's derivative, which is negative 1 over 2 sine of 2y. Okay, so when they want me to put 1 in for all the x's, remember that's the x coordinate. Okay, they want me to put that 1 in for all the x's. I don't have any x's, I have y's. So that means I have got to find the y value of my inverse, which means I need to find the x value of my original function. So I'm going to go back up to the original. This is my f of x equals cosine of 2x. So this is the x coordinate for my inverse, so it's the y value for my original function. So, oopsie, 1. Okay. So we want to find out where cosine is equal to 1. Well, that's going to be where 2x is equal to 0. It's also at 2 pi, but 2 pi is not in our interval. So that's going to be where x is equal to 0. So this is the x coordinate for our original function. So this is the y coordinate for our inverse. Okay, so x value for f, y value for my inverse. Okay, so I'm coming back over here and I'm putting 1 in for, or 0 in for all of my y's. So that's going to be negative 1 over 2 sine of 0. Well, the sine of 0 is 0. So 2 times 0 is 0. Oh my goodness, this is undefined. Craziness. Okay, so if you can't solve for y, that means when you take the derivative of your inverse, you're going to have y's, which means you have to find the y value for your inverse, which is the x coordinate of your original function. Now, since we've been talking about derivatives, we kind of need to go back over maybe another way to find out if a function has an inverse. This is another way to determine if you are 1 to 1. We find a lot of derivatives. We might as well use it to help us figure out if it's 1 to 1. So to show that a function is 1 to 1, we need to show that it's monotonic. Monotonic means it is strictly increasing or decreasing. So you're strictly increasing or you're strictly decreasing. Monotonic functions have inverses because they are 1 to 1. So they're going to give us maybe a little function here and show that f of x is strictly monotonic on the indicated interval and therefore has an inverse. So we need to show that it's strictly increasing or decreasing, which means we need to find the derivative and find those critical points. So we're going to find the derivative. And oh, how nice is it to have a nice little break about finding derivatives. It's 3x squared minus 12x plus 12. Oh, so nice. I'm going to set that equal to 0. I'm going to factor. So I've got x squared minus 4x plus 4. So when I factor that, I get x minus 2 times x minus 2, which is x minus 2 quantity squared. So my only critical point is that x equals 2. Well, we know that when we look at our derivative, when the factor has an even power, it's not going to alternate. So if I put a point in there, I'm going to be positive on both sides. Now, anytime I'm talking about increasing, decreasing, I have to talk about a sentence. So in order to show it's monotonic, I have to talk about my derivative. So my derivative is greater than 0 from negative infinity to positive infinity. So f is, notice the word strictly. Oh yeah, we are doing it. Strictly increasing from negative infinity to positive infinity, and therefore monotonic. Yeah, super. All right, so see, that wasn't so bad. It's almost as fast. If you didn't have to write the sentence, it's almost as fast as graphing it or doing the f of a equals f of b. Okay, let's do another. Okay, we have to show if it is monotonic, has the inverse. So when I'm looking at this, this is cosine of x over 2. What do you not notice? There's no interval here. What do we know about cosine, sine, any of the trig functions? Yeah, they are not one-to-one, but they want us to show if it is monotonic. So here we go. I'm going to find my derivative. The derivative of cosine is negative sine, and then multiply by the derivative of your angle, which is 1/2. So this little function is negative 1/2 sine of x divided by 2. Now we know that that is not monotonic. Okay, we know it's increasing, decreasing, increasing, decreasing, but we still have to show it. So if I go ahead and set this equal to 0, I'm just going to make a little piece of the graph here. I know that x divided by 2 is going to change my key points because now my period is 4 pi, because it's 2 pi divided by 1/2, so the period's 4 pi. So that means my key points here are 0, pi, 2 pi, 3 pi, and 4 pi. My amplitude is positive 1/2. Oh, let me keep that in red. So positive 1/2, negative 1/2. Okay. Now sine normally starts at 0 and then goes to the up version, but because it's negative, we're still going to start at 0, but we're going to go down and then back up. Okay, so this is a picture of our derivative. So we can see that the derivative is positive and negative, so it is not strictly increasing or strictly decreasing, therefore it's not going to be monotonic, but we need to write out our sentences. And I know that's pretty much your favorite thing to do. So I'm going to say the derivative is less than 0 from, yikes, that was a terrible one, from 0 to 2 pi. So f is decreasing from 0 to 2 pi. The derivative is greater than 0 from 2 pi to 4 pi. So f is increasing from 2 pi to 4 pi. Since f of x, or since f is not strictly increasing or decreasing, it is not, let's say f is not, now that looks like if, doggone it, okay, f is not monotonic. And therefore has no inverse. Okay, now when I was here, I could have said it is not monotonic, but we're talking about derivatives, we're talking about original functions, so try to stay away from the word it. It just can be no good coming from it. Okay? All right, so 18 here, when I look at x minus 4, quantity squared over my interval, I'm going to find my derivative using the chain rule, so that's going to be 2x minus 4 to the 1 power times the derivative of what's inside. So I'm going to find my critical points. Now, my critical point, that was my phone in case you heard that. My critical point is at x equals 4. So when I look at my interval here, now, my power is odd, so I would alternate, but look, they have chopped my interval down. So I am only positive on this interval. They're only talking about that interval. So that's the only interval I shall talk about. So my derivative is nuts. My derivative is greater than 0 from, and I'm going to use a bracket because that's what they did up there, and that's the only interval they want us to talk about. So f is strictly, try to fit that word in as many times as you can. F is strictly increasing from, wow, my handwriting's getting worse, sorry. And therefore monotonic on the interval. Now I slipped in that extra interval there, and that's because I want people to know that I know it's not monotonic over the whole entire real number system. It's only monotonic on the interval they chopped us down to. So I want to make sure that I have stated it again. Now on the other one, that wasn't monotonic, so I didn't have to put it. This one was monotonic on that interval from negative infinity to positive infinity, so I didn't feel like I had to write it again. But on this one, I want to make sure everybody knows, the AP graders, my fabulous teacher, she's so pretty. Anyway, I want to make sure that everybody knows, I know, it's just on that interval. All right, so we have learned how to find the inverses, derivative. We found another way to find out if a function is one-to-one and therefore has an inverse. It's been a great, great day. So clearly, I need to go because I am stumbling over all my words. I'll see you tomorrow.